Can we do the same thing for a pendulum?
Of course we
Yes. Okay, now remember with the spring, what did we do? We related second law, mass times acceleration, to Hooke's law. Hooke's law was talking about the force, the actual force that was causing it to go back to equilibrium, right? So we're going to try to do the same thing for a pendulum now. For a pendulum, it's going to be a little bit more difficult. Okay, so here's equilibrium. Here is not equilibrium. Okay? What exactly is the force that's taking it back to equilibrium?
Centripetal and attention.
What direction is centripetal force?
Upwards. Towards the
Is the centripetal force taking it back towards the equilibrium? Okay, so we don't want centripetal. Gravity is helping, right? Gravity is doing it. Gravity is down. Okay? But not all of gravity is pushing it in that direction, is it? Some of gravity is dealing with the tension and the centripetal force. So what exactly am I looking for here? I'm looking for the x component. If I rotate this, right, what I'm looking for is the component that's going perpendicular to my tension there. That's the piece I want. All right? That's the piece of it that I want. So if I redraw that down here, so we've got force of gravity. If I redraw that component right here, here's theta, here's my angle. What is that side, that x component that we were referring to? So the hypotenuse is the force of gravity, or the weight. IB likes it if you define it as weight instead of the force of gravity.
Sine.
Can you see that it's the opposite of theta? Okay, so sine of theta is equal to that side that we want over the hypotenuse, which is the weight. So if I multiply by weight, I get weight sine theta is equal to that piece that I want. That's the force that's causing it to go back to the middle, that component, that piece. This is why I wanted the SLs to see, because I'm reminding you of components, the forces, right? This is something that you've seen before. You need to be reminded of these things. Kinematics is going to be in everything. As you found out in some of your practice questions and possibly some of the questions on celebration, kinematics is everywhere. You're going to see it. Okay? So that's the force that we're looking at. So we're going to take that force, the weight. How do I get the weight?
Force mass times acceleration.
So the mass times the acceleration of gravity. So that's the weight times sine of theta is equal to
X.
mass times acceleration, right?
Yeah.
Because x was the force. X was the restoring force, this force that was causing it to go back to equilibrium. That will be equal to mass times acceleration, yes.
And can the mass cancel out?
Now the mass can cancel out, leaving me with g sine of theta equals a. A over G. Yes, we could solve that. We're going to wait just a minute because we did something earlier with A. Do you remember what we did in the spring one?
We replaced max acceleration.
We replaced A with the max acceleration. Now, before we do that, we're going to make a small change because, I don't know, as much as I love trig functions, I prefer for it not to be there. Okay, so what we're going to do, remember when we did the double slit interference? And we made that approximation for small angles? And we said that for small angles, we could just use a ratio instead. That's what we're going to do here. Okay, we're going to use some kind of ratio that's going to allow us to do a little bit better. Okay, so what we've got is we've got our angle here. This is essentially, well, this is the length. What would this distance be? X.
It's not a right triangle.
Wait, it's not a right triangle?
Because the L's are the same, so it's an isosceles
It
shape.
is x. It's the maximum displacement, right? It's how far have we been displaced from the center?
I do it.
It is x. Okay, so that's our maximum displacement, which is x naught, and this is done.
Every time.
That's blue.
There we go. So that is x naught. Okay, so I'm going to make the assumption sine is supposed to be opposite over hypotenuse. So we're going to say that this is just x naught over L. Now this is really an approximation because this line shouldn't be straight, right? This line should be curved because it's following a curved path. But if this angle is small, say less than about 10 degrees, and I'm using degrees because it's something that works well in our brains. If this is less than 10 degrees, then we can just make the approximation that it's just XO over L. Okay? So we'll change the sign of theta. So we'll go G times XO over L equals A. We talked about A need to be replaced by the maximum acceleration, so negative x. So G x naught over L equals negative x naught omega squared. Oh, we forgot to mention here, G is gravity.
9.8.
If the displacement is to the right, what direction is the force?
To the left.
To the left, so I apologize, this should have been a negative all along. Okay, so what can I do here?
Cancel the negatives.
Cancel the negatives.
Cancel the x naughts.
Cancel the x naughts. And so I'm left with G over L equals omega squared. But again, omega is kind of fuzzy in my brain, so what do I want to change it to?
Period.
To period. So I'm going to do, remember the period
2 pi
was
over t.
2 pi over, yep, and omega was 2 pi over t. T is 2 pi over omega. Remember, I just multiplied by the t divided by the omega. And so again, I'm going to go here, and so we'll go G over L equals 2 pi over t squared. Solve for the period. Again, take the square root. Multiply by t, multiply by the reciprocal. So I get t equals 2 pi square root of L over G. You may remember that when we looked at pendulums, I asked you guys to figure out whether mass mattered or not. Did mass matter?
No.
Did. You did a lab on that. You came up with your own procedure. You showed that length didn't matter. Or sorry, mass didn't matter. What does matter? Length matters. All right, so we find out that length is the thing that matters. What else matters?
Gravity.
Gravity. Think with the spring, we had the spring constant, right? Which is something specific for a spring that caused the force. What is causing the force of the pendulum? It's gravity. And so that's why the gravitational constant matters. It'll be different on